Okay, as I was saying, density in unit conversions is one of the things that is covered in terms of materials properties on our end of course test, partly because it's one of the things that is testable. Now, our bridge, our sticks of wood are 3/32 of an inch by 3/32 by 24. Okay? Most of our bridge, we have done we're building it, and our constraints are metric. So 3/32 of an inch. Okay? And we want to change that into centimeters. How many centimeters are in an inch? Huh? 2 point something. Yes, 2 point something. 2 point what? 2.54. So we got 2.54 centimeters is in 1 inch. Okay, so, and again, when you do your unit conversions, we set it up kind of like the field goal posts or as fractions. We can do dimension analysis to make sure we're canceling what needs to be canceled. We're starting with inches, changing into centimeters. So therefore, the inches goes on the bottom, centimeters on the top. So 3/32 times 2.54, what is that? Calculator? .238, yes. 0.238. Okay. So then the other dimension we need to switch is the 24 inches. So 24 inches over 1 times 2.54 centimeters over 1 inch. Again, dimension analysis lets you know that you are doing the conversion in the right order. Let's go ahead and calculate that one. 24 inches to centimeters. 60.96. So if we use 3 significant figures, which would be plenty in this case, and I'm going to pick 3 because of the 2.54 centimeters to an inch. So 3 significant figures, that would round at 61. Does that make sense? I know in math class you do a certain number of decimal places. In science class you do significant figures. In engineering we do what makes the most sense. So sometimes we do, so I would probably round that 61.0 would be 3 sig figs. So the volume of 1 stick of basswood. The volume of 1 stick, length times width times height. Now that's 3/32, which is 0.238 times 0.238 times 61. So 0.238 times 0.238 times 61. And I did the calculation wrong. What do you get? Three significant figures. What do you get? .455, which 3 sig figs would be 3.46. Now that is centimeters cubed. Now, what is density? Density is mass divided by volume. And by the way, this whole calculation we're doing now, you're not going to have to redo this one. That's why if you're taking notes on this, you'll be ready to do yours. We'll use one of my bridges as an example. The density is mass divided by volume. And wood grows at different rates, has different moisture content, and it varies a lot, okay? So basswood, one of those sticks will weigh from 1 gram all the way up to as much as 2.2 grams. So that varies a lot. So the thing that makes the most sense is the average of all those pieces. The average of that would be like 1.6. So if we do 1.6 grams divided by 3.46 centimeters cubed, that's your mass divided by volume for your density. 1.6 divided by 3.46, okay, that is 0.462. And the units on that would be grams per centimeter cubed. Okay, so that's your average density of basswood. Okay, and one of the things that helps with having a good bridge is having the bridge be a consistent weight throughout. So that way, if there's equal forces, heavier wood is technically stronger, but it is a efficiency competition. So most of you are going to have like 1.5 or 1.6 gram sticks of basswood. Okay, I take out the real heavy stuff and the real light stuff. So we're kind of left in the middle. Okay? So that's the density of one. So that's how we find the density. Now again, talking about this, oh shoot, I lost my picture. When I cleared the page, I lost the picture. Let me pause the recording a second. I gotta get that. Okay. All right, so there's one of my bridges. Just a basic mooring truss. And what I'm worried about is just getting an estimate for the bridge. Now, the bridge is made up of 2 trusses and connecting pieces. So what I need to do is just take a ruler and my drawing and get estimated lengths for all the pieces, because the volume times the density will give me an estimated weight. Okay, so real quick, I need to do some measurements. And this is what you're going to need. This is the part that's going to be different for your bridge. Yeah, I lost a couple fun caps. So what do I have? Estimated, that's 14. The bottom is 320 or 32, and that's centimeters. Oh. The top is 13. I should give this to one of you and let you measure. And then my triangular pieces, this is 10.5. That side's 11. That one's 11. That one's 10.5. And the other leg's a little bit longer. It's about 15.5. So all of my lengths to make up one truss. I've got 2 that are 14, because I've got that drawn, so I'm going to double that. I've got 2 that are 13. I've got 2 that are 15 and a half. I've got a 10 and a half. I guess I got 2 that are 10 and a half, don't I? 2 that are 10 and a half. They're just 2 separate pieces, not laminated. And then I got 2 that are 11. And 1 piece that's 32. Okay, so basically, you're going to just find the length of all of your pieces. So this is this one particular bridge. So now I need to do that calculation. 2 times 14 plus 2 times 13 plus 2 times 15.5 plus 2 times 10.5 plus 2 times 11 plus 32. So that gives me a total length of 160. Okay, now what's the volume? The volume of all the pieces for one truss. And I did ignore this little piece here, because that's kind of a gusset piece. I didn't worry about these tiny little pieces here. All we're doing with this is getting an estimate. If those were longer than a couple centimeters, I probably would include those. Okay, but those pieces were a little short. So I wasn't too worried about that. So then the volume would be length times width times height, which I've got 160. That's the length of all my pieces. And then what was my metric was 0.238. And I'm not worried about the little triangular cutoffs. This is just going to give us a pretty good estimate. So 160 times 0.238 times 0.238. That is 9.06 centimeters cubed. So then, if the density is the mass divided by the volume, okay, how do I solve that equation for the mass? What do you got to do? What do you have to do to solve that equation for the mass? That's algebra 1. D equals m divided by v. What do we got to do? Huh? V times d. You got to multiply by the volume on both sides. So that's going to cancel out. So the mass will be the volume times the density. So I have 9.06 times, and then we found the density. The average density is, we found that all the way at the top, 0.462 times 0.462, and let's see, 9.06 times 0.462, that is 4.19 grams. Okay, so that's the average. And that's just an estimate. Let's see, I have that actual bridge. I have a second sample. I have that actual one built. So if I weigh one of the trusses on the scale, I have to turn the scale on, I'm getting 4.9. Okay? So the actual weight that I got for that, I'm actually getting, so this would be an estimate for one side. Actual, I'm getting 4.9. Now, I know you can't see this in the video, but I already have gussets glued on this, plus those couple other little pieces. And the gussets actually add a lot of weight. And if you notice, if you look at my gussets, I took the Dremel and I sanded them down to about half or third thickness even. So that is accounting for that extra weight. Plus the glue also weighs something. And the more glue you use, if you use too much glue, I think I talked about this the other day, if you use too much glue, your bridge will weigh 35 grams because you got gobs and gobs of glue on. Okay, it'll be way overweight. Okay, the other thing to note on those gussets, I lost about an entire gram of weight off the truss by sanding the gussets down. That's a lot. That's a significant amount by sanding the gussets down to less thickness. Okay, one year I had somebody who got third in the bridge competition, would have been second if he would have sanded his gussets. Now I lucked out because I would not have been excited to go on a field trip to wherever it was out of state that year with that particular student. So I sort of lucked out. But anyways, yeah, he would have been second place had he sanded his gussets. So that estimated. Okay, what do we want to do with that estimated number? That is one truss. So to estimate the total bridge, okay, to estimate the total bridge, take one truss. And I've been doing this a long time. It usually comes out pretty close. Times 3. Now, why are you taking one truss times 3? You got 2 trusses, plus you have the connecting pieces. Yeah, where are you putting your load on? And I don't have this one finished yet. I have the other one finished. So when you put the bridge together, I do have the other one finished. You know, we've got connecting pieces which are called struts, or the diagonals that go between the 2 sides are torsional supports. Those diagonals that connect the 2 sides keep it from twisting. If it starts twisting, it will fold up like an accordion when you put a lot of weight on it instead of breaking. So then it doesn't hold as much either. So if I do that, that is 4.19 times 3, which would be an estimate of about 12.6. I rounded up a little bit on the 4.2, I think. Yeah, 4.2 times 3 would be about 12.6 grams. I'll bet I come out pretty close. Now, the other bridge that I did this with, I estimated 15 grams. It actually came out at 12.5. But we would rather have an overestimate a little bit than an underestimate. Again, you have to be under 25 grams. So if you do this calculation and you're at 24, 25 grams, you probably have either made a calculation wrong or you have too much material in your bridge. Okay? The national winners typically have around a 10-gram bridge or under 10 grams and hold 50 kilograms and end up with a efficiency of around 5,000. Okay, so both my bridges are probably a little bit overbuilt. Something needs to be a little bit less in order to have that 5,000 efficiency. I don't know how good the designs are. That's one of the things we'll still have to test. Okay, but that's how you do a mass estimate. So I'll record this video if you need to go back to it. I also have a PDF of this uploaded on Google Classroom. I'll put this video up as soon as it's done processing, so that if you need to watch this again to do your mass estimate, and that will be like a 10-point assignment. Okay, and all you